Hello, good day. Can you guys hear me through the microphone? Okay, welcome back. I think I will start. And I'm going to start with a digression. A digression, just a digression. Let's begin with a digression. Okay. We are going to be going into integrals in R3 today. We're going to be studying integrals in R3. So, as you saw in integrals in R2, I had to know something about curves in R2 because the curves form the boundaries of domains. So what's going to happen in R3 is you need a boundary of a volume. And so those boundaries will be surfaces. Okay? And I like to do this little discussion at the beginning just to remind you of surfaces a little bit. Okay? So in general, a surface is given by some function s, so a surface in R3 is given by given by terrible handwriting, given by a function s of x, y, z is equal to 0. Okay? It's given by a function. The way you think about it is R3 is 3 dimensions. If I make one equation that relates x, y, and z, that is one constraint on the 3 dimensions, right? You can choose any x, y, z, but you put one constraint. So you can't choose them independently. That's one constraint. So you go from a 3-dimensional system to a 2-dimensional system. If you put 2 constraints on that, that would be 2 surfaces. And I would have 2 surfaces, and if you wanted to solve them simultaneously, you would solve at the intersection of 2 surfaces. One 2-dimensional object and another 2-dimensional object creates a curve, which is a 1-dimensional object. Okay? And if you have 3 such surfaces, whack, 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 you have surface, surface, create a curve, intersected with another surface, would in general be at a point or a collection of points. Okay? And that's a very general, just kind of envision that idea. You can imagine multiple surfaces intersecting. Now, so you can imagine arbitrarily complicated surfaces, and we will be studying some complicated surfaces. But for a moment, I would just like to talk to you about the simplest class of surfaces you could start with, which is basically linear. I hope you can see this. Linear surfaces. Linear surfaces. They fixed it. Oh, that's so nice. Linear surfaces. Very good. So just like when we talk about the simplest class of curves, we start with the lines. Why not start with the lines, the linear surfaces of for 2-dimensional surfaces in R3? So a linear surface would mean that this is a linear function. Okay? A linear function of x, y, and z. So the most general linear function I could write here is ax plus by plus cz. And I'm going to write this with a minus d is equal to 0, where a, b, c, and d are all constants. Okay? A could be, you could just, whenever you see too many variables and you need to make it a little more definite, just put everybody equal to 1 for a second. 1, 1, 1, 1, 1. Okay? So this is a surface. So, by the way, this is going to be a flat surface. This is going to be depicted by a plane. This is a plane in R3. So this is a plane. And I'm going to tell you now that you're going to be taking linear algebra at some point. Most of you are going to be taking linear algebra 22A. And linear algebra deals with the intersection of one plane with another plane. And their intersection is not a general curve. It's a line intersected with a third plane. You intersect a line with a plane, and you got a point. If I were to have 3 equations for one plane, another plane, 3 such equations, their simultaneous solution would be a point. X, Y, Z, some number of X, Y, Z. And geometrically, that corresponds to the intersection of these 3 surfaces. Okay? So when you go into linear algebra, don't think of it as just a series of like mechanical manipulations, I'd like you to think about the geometry that you're actually being asked to envision, at least, okay? Spend some time thinking about the geometry of the whole thing. Okay, the way I look at this problem, Arturo, Christopher, Jingyang. The way I look at this problem is geometrically, and I want to show you a simple case here, okay? Look at this problem as follows. Consider d equals 0 to start, okay? Because it's nice to start with a simpler version of the problem. When d equals 0, what do I have? I have ax plus by plus cz is equal to 0. Now, we'll be getting into the details of this at some point when we get into chapter 16. But if I draw my x, y, and z coordinate space, what you see here is that x, y, z is a point. Here's the point x, y, z in this space. And there is a vector from the origin to the point, which is called the position vector. And often this will be denoted x vector. Okay? That's the vector that goes from the origin to any old point in the space. And this equation says, for the vector to actually describe a point on the surface, it must be related, the components of the vector must be related in this way. Okay? But when you look at this operation, you should scratch your head and say, oh, wait a minute. There's another vector sitting here. Okay? And look at the other vector. A, comma, B, comma, C is a vector. It's a vector. A, comma, B, comma, C. Okay? It's a vector. It's a constant vector. This is the position vector. It varies, right? For this point, it's some value. For this point, it's some value. For this point, it's some value. So I want x, y, and z to lie on the surface, and therefore they must satisfy ax plus by plus cz equals 0. And abc is a vector. Now look at what this says. Well, first, by the way, it says the origin is in the surface. The surface passes through the origin, because 0, 0, 0 satisfies 0 equals 0. That's good. So the origin is in the surface. But furthermore, I will note to you that if I write the vector ai hat, okay, plus bj hat, plus ck hat, that's the vector. That's the component written as components of, with the basis vectors I hat, j hat, and k hat, where I hat is the unit vector along the x-axis, j hat is the unit vector along the y-axis, and k hat is the unit vector along the z-axis. Okay? Always pointing up, always pointing right, always pointing forward, kind of thing. Then this equation right here, the equation for the plane, is an interesting equation. It says a I hat plus bj hat plus c hat, k hat dot product with x I hat plus y j hat plus z k hat is equal to 0. Is equal to 0. So imagine this. So let's do this with a line for a second, because I can draw this a little better with a line. Let's do this with a line. So let's imagine we're just doing this with a line in the xy plane. And here's a line. So I'm going to set ax plus by is equal to 0. Okay, so I'm just setting c and d equal to 0 so I can draw it a little better. So the position vector for a point on this surface is a vector that goes from the origin along this line to some point. Here's a position vector, x, y. There's the point. Okay, so look at this vector here. I want to make it bold. Try to make it bold. So you're going to distinguish the vector from the line. There's a vector to the point, and then there's the whole line. Okay? And the line is just a simplification of the plane. And this equation says that a I hat plus b j hat dotted into that position vector xi hat plus yj hat is equal to 0. And that is a statement that the position vector, so this says this vector is perpendicular to this vector, to the position vector. And this vector has a name. It's the normal vector. This is the normal vector. So this is what so ai hat, we'll call this the normal vector. N vector is equal to ai hat plus bj hat. It is the normal vector to this surface, or to this line right now. And you can see that very quickly. This is the vector ai hat plus bj hat. And you can move that vector anywhere along the surface, and everywhere this vector is perpendicular to the position vector, which gets you into the surface, into the line. So when you look at an equation of that form, what you should see is there's a normal vector dotted into the position vector. So that now that tells you that the components A, B, C tell you how this plane is oriented, because it gives you the perpendicular to this plane. Okay? Does that make sense to everybody? Who's seen that before? In 21C, you should have seen that, right? Okay, so I kind of got a little boring there. Sorry about that. And the other thing to note is, okay, so that's how you do it for a line. It'll show you really quickly. I mean, in this case, you would agree that maybe x equals negative a and y. So if x equals negative 1 over a and y equals 1 over b, that should be a point in the plane, right? And so I should be able to show you that negative a and 1 over b, fits that description, but it does, so there you go. It's perpendicular. The other term, the d term, just to point out what the d term corresponds to, the d term corresponds to a shift, okay? So I'm now going to give you a more general way to think about a surface, a plane in particular. In general, a plane is described by the normal vector to the plane dotted into the position vector in the plane minus some constant vector x0 is equal to 0. That's the general form of a plane if you want to think about it geometrically. Because if you write this out, you say n is equal to ai hat plus bj hat plus ck hat. And x0 is equal to x0 I hat, x0 vector is x0 I hat, plus y0 j hat, plus z0 k hat. If you write it out like this, then you can put it in the form that I first put up there, which is ax plus by plus cz. That's the left-hand side over here, and I'm going to bring this over to the other side, is equal to ax0 plus by0 plus cz0, and that's what we call d. The constant. That's just some constant. It doesn't depend on x, y, and z. It's some constant. And so when written this way, you can see that this is a surface, a plane, whose normal vector is n, and which passes through the point x equals x0. Because when x equals x0, this is clearly 0, so the whole thing is 0. Okay? So that's the algebra and the geometry. That's the algebra of planes and the geometry of the algebra. That's what you're seeing, okay? And by the way, what you're going to be doing in linear algebra is really considering how the matrices are really an expression of these normal vectors all the time, okay? So that's what you're going to be getting into. But I wanted to talk about that because I really want to talk about integration in 3 dimensions. And we need to know basic surfaces to understand the boundaries of integration in 3 dimensions. So here we go. Integration of functions over a domain in R3. Integration of functions over a domain in R3. I think this is section 15.5. It's all the same, everybody. Okay? So now we get into where my drawing starts to fail you enormously. So a little bit, you have to watch me draw it, because as I narrate it, I hope to make sense of it. So that's the canonical jelly bean domain. Now it's a true jelly bean. It's a three-dimensional object that you may wish to sink your teeth into. And you want to consider a function. So this is the domain D. Okay? There's the boundary of D is some curvy surface. Pardon me, the smoke's gotten to me this last couple of days. You think of the boundary of the domain as some curvy surface. And what you want to do is, and to this you add a function. Consider also a function so we always have to have that other function, f, which is a function of x, y, and z. Okay? Now, folks, in mathematics, we always introduce shorthand. Okay? So now we're going to start introducing some more shorthands here. Okay? So I'm going to tell you the first shorthand notation. I will often write this f of x vector. All that means is they're synonyms. Because this is truly three arguments, right? X vector is that position vector. It's xi hat plus yj hat plus zk hat. And all that means is, what this means is you give me three numbers, and I spit out one number. The way I think it's very convenient to think about it is you give me your location, and I'll tell you the temperature. You give me your location, and I'll tell you whatever that is, OK? So we want to understand, we did integration in one dimension. We did integration in two dimension. Now we want to give meaning to this object, the triple integral. Okay? The triple integral of f of x, y, z with respect to v. So I foreshadowed all of this already. And I hope what I'm about to say makes complete sense to you. Okay. The idea is you have a function at every point in space. But what you do is you take this domain and you chop it up into small pieces. Sounds familiar? That's all you're doing, right? You're chopping it up into small pieces. You measure the volume of each of those pieces. And you evaluate the function at any point in each piece. Okay? You have a little cube there. You can evaluate at any point in that piece. Then you take the product of the function evaluated at that arbitrary point, multiplied by the volume of the domain of that subdomain of that little piece. You multiply it for each of those little pieces, and you add up the result from I equals 1 to n, where n is the total number of pieces. And then, on a computer, this is where you stop. You just make the pieces small. You just say there's a lot of, n is big, the pieces, the volumes are small. But in calculus, we say, look, there's a way to take the limit that the partition size goes to 0. And the partition size, in 3 dimensions, what can it be? Well, the partition is the choice of chopping, is the way you chopped. Okay, and technically speaking, the partition is the set of sets, the set of sub-volumes that you've created. And the size of the partition is the biggest delta VI that you have. Okay? I'm going through this fast because nothing is different in 1D and 2D and 3D. Right? It's all the same stuff now. That's how we define the integral. It's just that you got to find a way to measure volumes. And so this is kind of like boring right now. I hope it's boring. I hope it's so boring for you that you're going to just crank through it and be able to do all this stuff really easily. You have now an arbitrary way to chop this volume. Chop, 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 chop. But of course, we don't chop with like a melon baller when we chop a ham, right? We slice it this way, up and down, and then we slice it this way, and then we slice it that way, if you want to dice your ham, right? We chop it into little volumes, okay? We have a pattern of chopping, and we use the plane, which is the plane of the knife, which is parallel to the coordinate planes, right? X equals constant, y equals constant, z equals constant, okay? And so we exploit the same thing that we did in 2 dimensions, which is Fubini's theorem. So effectively, we have Fubini's theorem again. And what is Fubini's theorem but simply an order of operations? Fubini's theorem is simply an order of operations. And so let's do it as though we're doing the z integration first, okay? So when you chop all this up, each of these little rectangular prisms have a delta x, so there's a delta x this way, a delta y this way, and a delta z this way. So their volume, delta vi, is equal to delta xi times delta yi times delta zi. The horizontal width, this is when you create these little volumes, right? I really don't want to belabor this point because I want to get to some examples, and this is a little, this is theory that's almost too easy at this point because you understand that, you know, there is a delta x, delta yi, delta xi, and delta zi, and you're going to have a point in here, some point inside that domain, okay, and that point has xi, yi, zi. That's the coordinates of that point. And you can evaluate the function at that point. So the issue is you fix your x and y, and you do your z integration first. So that's like taking this kind of rectangular tube, right? And you're going up here. You evaluate the function all the way as you go all the way up. And then when you do that, you're going to be left with a function of x and y. And then you just have a 2D integral to do. So algebraically, this says the triple integral over the domain of f of x, y, z, with respect to the volume over the domain is equal to, we're going to integrate from some z bottom to z top of f of x, y, z, integrated with respect to z. Then we're going to integrate from some, say, y bottom to y top, and then from some x bottom to x top. And I'm using bottom and top all the time because the bottommost value to the topmost value is what we mean. And this is going to be dz, dy, dx. This is the statement of Fubini's theorem in 3 dimensions. But how does this work? You're going to integrate from z bottom, but z bottom can depend on where you are in the xy plane. It's a surface. It's some lower surface. So in general, this will depend on x and y, and this will depend on x and y. In the case that it was a plane, I had a plane equation, ax plus by plus z equals 0. You just solve that for z of x and y, as you would in any other instance. That was an implicit relationship. You would make it explicit. And of course, what results here is that the z is integrated out, and you've got just some complicated function of x and y now. More complicated, or simpler, or whatever the case may be. This results in a function of x and y. So you squint, and you're like, hey, that's just a 2D integral now. And I know how to do that. And so that's just y bottom as a function of x, y top as a function of x bottom, and x top. That's how you do this. That's 3-dimensional integrals. That's it. It's an iteration of 3 single integrals. The art of this problem, the kind of squint and look strange at this problem, is that you have to figure out your z top and your z bottom, your y bottom and y top, and your x bottom and x top. It's finding those bounds of integration that's the issue. Okay? It's not a hard issue. Some of the questions in the book are, they give you graphical representations, and I'm going to do a couple questions right now for you. Okay? Is that cool? Does anybody have any questions before I start doing examples? I know we all like when I do examples, but I also want to give you a little bit of background. There's tons of examples in the book. Is this thing on? Huh? No? It's a green light. They say, are you guys, well, whoever's seeing, sorry, whoever's ever seeing, I don't know if anybody's looking at the videos. How about I shut this off? Okay, the first thing I'm going to do is say, if the function is equal to 1, the number 1, the pure number 1, and I'm in a space of meters, which is literally physical space, x, y, and z, what am I measuring when I calculate the integral? Sorry. I set you guys, set at least one of you guys up for failure. The volume. If the function is equal to 1, the definition is, so that's a function just equal to pure number 1. That is the limit as the partition size goes to 0 of the sum of 1 times each of the volumes. That's just the total volume. And that's a really common thing to calculate because we're interested in total volume, right? So let's see. Let's calculate volume. Let's calculate. This board is no good. This board is just no good. Let me try another board here. Let's calculate a volume. Okay? So what should we do first? I'm going to not do the trivial one. Let's do something interesting. Let us imagine, let's imagine that we have x, y, and z axes. Okay? Yes? I know, it's really bad, isn't it? Sorry about that. Thanks for telling me. Is it better? Da-da, no ruffle? Very good. Thank you. Okay. Let's see. So now we're getting into me drawing in 3D, and even though I've been doing this for ages, I still don't do that well. So what I want you to imagine is a plane that's cut this way, okay? Would you guys prefer if I use letters or numbers? Who says numbers? Put your hands up. Who says letters? Everybody who put their hands up the first time, you fail. Just kidding. 1, 2, 3. You want numbers? I'll give you numbers. 1, 2, and 3. 1 meter, 2 meter, 3 meter. Okay, so so when you want to understand the general form of volume of this shape, you'll have to do this a million times. Those of you guys who wanted me to use letters would just do it once and understand how it scales. But nonetheless, you want me to work hard. So, okay, now first here. What is the volume? So here's a legit question. What is the volume below this plane, bounded by the z equals 0 plane, the coordinate plane, z equals 0, y equals 0, and x equals 0. Okay. This is z equals 0, this is x equals 0, that's y equals 0. So what is the volume there? Well, the first thing I have to do is tell you what that plane is, right? So we better get an equation for the plane. And if you take a look at the plane, this is very important. Now hear me very carefully this one. If you were to come from above, look down on that plane, okay? That plane would have only one, it would have a uniquely defined upper surface and a uniquely defined lower surface, okay? Now imagine all sorts of things you could do about bending that top point and moving it, right? If you just take that triangle, imagine in your head, you move that top point, and then there's going to be another plane over here. There'll be this lower plane, and then there'll be that side plane. There'll be all these other planes that might extend, depending on how you stretch it, okay? By holding that lower plane fixed. What I'm saying is that this is a more straightforward question because z bottom is the same under where z top is everywhere the same. Okay? A singly defined z top and a singly defined z bottom. Okay? It has what I would call a very simple shadow in the xy plane. Okay? Now, let's write the equation for this plane. I've stalled enough. How do I do this? Well, does this plane go through the origin? No. Okay? But I know that it goes through these 3 points. So I'm going to write the general equation for a plane, ax plus by plus cz is equal to d. I don't know what the answer to this is, guys. I just made it up, as you saw. So I have to go through it. I have to go through the steps, okay? So what I have to do is recognize that it goes through each of those points. So it goes through all the points. Okay, so this point here is 1, 0, 0. That's 1, 0, 0. This point is 0, 2, 0. That's this point over here. And this point is 0, 0, 3. Okay? And so that's 3 equations. Let's substitute, we're going to substitute the point into the expression for the plane. And each time you substitute, you'll get 1 equation, so you will get 3 equations. Let's look at those 3 equations. The first equation says A equals D. You see that? Because 0, 0, A times 1 is A equals D. The second equation says 2B is equal to D. And the third equation says 3C is equal to D. Okay? Now I'm going to plug, so I have 4 unknowns, A, B, C, and D, but I only have 3 equations. So we have what appears to be a problem, but you'll see it's not actually going to be a problem. Okay? Why? Well, let's substitute them into that equation. A is equal to D, so I'll just write A is equal to D. That's dx. B is equal to D over 2, so that's plus y times D, plus dy over 2. Let's write it dy over 2. Plus a C is equal to D over 3, so this is going to be dz over 3. Okay? Is equal to D. And this tells you something else that's neat about the equations for a plane. If D is non-zero, you can always divide by D, and you don't actually have 3 independent, so you don't actually have 4 independent parameters, you have 3 independent parameters. Because D can always scale out of the problem. So the equation for this plane is x plus y over 2 plus z over 2 is equal to 1. So that's the equation for the plane, for the upper plane. Okay? Does that make sense? Yes? Yes. Thank you. Sorry about that. Now, what the integration asks us to do is say, go to a fixed x. I'm going to do z first, okay? It says go to a fixed x and go to a fixed y, and you make a little kind of rectangular footprint there, and you're going to go up. You're going to integrate up in z. This is a lot of things to see, and I don't even know if the video can possibly capture any of this. And then you're going to integrate up to the plane. So you're integrating up along these kind of rectangular parallelepipeds, rectangular prisms. And that's what it looks like. So what are you going to do? You're going to say, well, the integral over this domain of the number 1 with respect to v, which is equal to volume of the domain, is equal to, I'm going to use Fubini's theorem. I'm going to go from some z min, which is a function of x and y, to z max, or z bottom and z top. Sorry, let's stay with the same notation. Z bot and z top. Z top. okay, dz. And then I'm going to do the y integration. And then I'm going to do the x integration. And I'm going to go from y, goes from y min, y bottom, sorry, of x to y top of x, its maximum value. X goes from x bottom to x top. That's how you set it up. Okay. And just as before, the issue is to figure out what z bot, z top, y bot, y top, x top are. Well, I hope it's quite clear in this case. Okay, you're going to use Professor Bielow's all-time, always going to work. It's harder to do in 3D, right? It's harder to do in 3D. You put your chalk down here, make a little smudge at the bottom for that little rectangular piece. You go from the bottommost all the way to the topmost. It's pretty clear in this case that z bottom is equal to 0, and z top is on that diagonal plane. Is it not clear? If something's not clear, tell me. If you guys have got different jokes, it's fine. Did I say something that wasn't clear? No, we're good, we're good, okay. So z bot is 0. And by the way, that's the plane, z bot of x and y is equal to 0. That's the whole plane. That's the whole plane. Z top of x and y is on that plane right here, on this diagonal plane. This is an implicit expression for x, y, and z. You need z in terms of x and y, because we chose to do z in terms of x and y first. Okay? So to get z in terms of x and y, you just solve for z. And because it's a plane, it's trivial to solve for z. It's super, super easy. Okay? That's going to be 3. It's super easy for you, not for me. Minus 3x minus 2y over 3. I think, no. See, I said it wasn't going to be easy for me. 3 over 2. Okay, I just rearranged that. Now, folks, what I did was I started on this plane and went up, right? I could have done start on this back plane and go forward. And that would have been the x integration first. I could have done start on this back plane and go this way. And that would have been the y integration first. Whatever, it doesn't matter, right? It can't matter. Mathematics, it just cannot matter which order you do in these kinds of operations, because they are additions and multiplications. Okay? So the order of the addition had better not matter. So I'm just going to do this example. Okay, so there's z bottom and z top. Now, how do I find y bottom and y top? Well, when you look at this, and now you look at it from above, you see quite clearly that there is a triangle in the xy plane. You see that triangle in the xy plane. Okay? Now, I'm going to integrate from y bottom to y top. So you're going to do these integrations in that direction next. Okay? At fixed x, you go strips and y. So I need to know what, so now you use Professor Bielow's all-time going to work, put the circles and put the stars on it thing. So this is the y bottom. The minimum values of y bottom are along that edge of the strip. These are the maximum values. These are the values of y top along that thing, okay? So this back end is pretty clear. It's pretty clear that that's y bottom equals 0. But I want to show you something, that back end is the intersection of two planes, okay? That back end is the intersection of the z equals 0 plane with the y equals 0 plane. That thing is a line. That thing is a line, z equals 0 and y equals 0. So y bottom, which is generally could be a function of x, in this case is the simple function of x, x equals 0. Why did I tell you that it's an intersection? Because the question is, how do you get this line, the not so obvious one? I mean, it's not that mysterious what it is. You could probably eyeball it, but in general, it's not easy to eyeball. How do you get this curve right here? Okay? Well, take a look at what this curve is. This straight line, is the intersection of z top with z bottom. Okay? So notice that y top of x is a curve which lives on the intersection of the planes z top of x and y and z bot of x and y. This is an important conceptual thing that turns into an algebraic thing. Okay, so this is the concept that gives you the algebra that allow you to solve these problems over and over again. So the intersection of z bottom and z top, all that means is, I am so sorry about that. Sorry about that. The intersection just means the simultaneous solution, right? At an intersection, well, on the plane, z satisfies all these, it has all the values that satisfy the points on that plane. And on the other plane, it satisfies all those. When you simultaneously satisfy them, it's at the intersection. So at the intersection, z top, so z bot equals 0, and z top equals 3 minus 3x minus 3y over 2. At the intersection, this is equal to z, and this is equal to z. So that clearly tells you z equals 0. And then you substitute that in here, and that says 3 minus 3x minus 3y over 2 is equal to 0. Okay? Now that's trivial algebra when it's in the case of planes. But it gets more complicated if you had circles or other things like that. Okay? And then, of course, you solve this, and you're left with, I divide through by 3, and I'm going to have y is equal to 2 times 1 minus x. That's this line over here. Okay? And you see that that makes sense because when x is equal to 1, y is equal to 0. When y is equal to 2, x is equal to 0. So these 2 points are in the plane, are in the line. So I hope we did it right. So that gives me y bottom and y top. And of course, now you know how to get x bottom and x top. It's pretty clear that x bottom is 0 and x top is 1. Okay? So let me finish the volume of this thing. Okay, so the volume is equal to the integral from x bottom, I said is 0. It's pretty clear from that picture it's 0 to 1. From y bottom, I hope you understood my argument that it's y bottom equals 0, the intersection of those 2 coordinate planes with the upper is y top is 2 times 1 minus x. And then from z bottom is 0 to z top is 3 times 1 minus x minus y over 2. And then I have to integrate that with respect to z, with respect to y, and then with respect to x. And for the first few times, I still encourage you to use parentheses to emphasize that you're doing order of operations. Okay? Since I'm just doing the volume, you see that all this, since it's the volume, the function here is 1. It's a trivial function. It's really easy to integrate. This thing is just the height of the top surface minus the height of the bottom surface. That's all it's always going to be. So it's z top minus z bottom. It's the height of each of these prisms, rectangular prisms. And so this first integral is trivial. It's 0 to 1. The integral from 0 to 2 times 1 minus x. 1 minus x minus y over 2. Then I have to integrate that with respect to y. And then I go ahead and integrate that with respect to x. And this is, now I have to remember how to integrate polynomials. Good luck to me there. So the integral of 1 minus x with respect to y is 1 minus x times y. It comes out of the front. Thank you. 1 minus x times y minus y squared over 4. And I have to evaluate that at 0 and 2 times 1 minus x. And then I have to integrate that with respect to x. OK? So I evaluate this. And I'm left with the integral. So I got the 3 out front from 0 to 1 of 2 times 1 minus x squared. That's evaluating the first term. Minus 1, so minus 4 times 1 minus x quantity squared divided by 4. And then I have to integrate that dx. And you say, oh, that actually works out kind of nice. So this is going to be 3. Just to finish that off, that's 3 times the integral from 0 to 1 of 1 minus x quantity squared integrated with respect to x. And I'm not going to do it. Just do it. It is what it is, OK? Because there's a 2, 1 minus x squared, and 4 over 4 is 1. 2 minus 1 is 1. There's the 1. There's the 3 from before. Now go back and do this with general points. OK? Do it with more general points and see what you get. Now you can have a formula for the volume of these kinds of shapes as a function of those points, which is actually a little more interesting. OK? OK. Now, we got 5 minutes. I can do this. Calculate the average of the distance squared of a point in a sphere to the origin of a sphere, and a centered sphere. So what I want to do is calculate an average. OK? And the average is going to be, I want to average the function. If this is supposed to be a sphere now, this is x, this is y, and this is z. I better give it some size. I'm going to make it radius capital R, 5 meters, 700 megameters. Which sphere has radius 700 megameters? .4 megameters. The sphere has radius 6.4 megameters. Calculate. What I want to do is average the function d squared. If I have a point here that has x, y, and z coordinates, then I can measure the distance from this point. This is a point supposed to be not on the surface, but somewhere in the sphere. I can measure the distance from this point to the origin. OK? That's the distance function d, and that's equal to the square root. So d is a function of where you are. Your distance to the origin is a function of where you are. And it's just Pythagoras' theorem, the square root of x squared plus y squared plus z squared. And because I hate dealing with square roots for now, later we will. It'll be fun. But for now, we're not going to deal with square roots. We just learned to integrate in 3D. I want to average d squared of x, y, and z, which is simply x squared plus y squared plus z squared. And with the average of this, and I've said this over and over again, the average of a function, so the average of d squared of x, y, and z, I denote it with an overbar. That's just notation. It says average this thing. And that has to be the triple integral over the domain of the function d squared of x, y, and z, integrated with respect to the volume By the way, sometimes I'll put a 3 up here to indicate that we're in 3 dimensions. Physicists would use a 3. Sometimes mathematicians do that too. Makes you remember that you're in 3D. Divided by the volume. Just as averages in 1D were the integral divided by the integral of the number 1, 2D was the integral of the function divided by the integral of the number 1 with respect to area, it's the same thing. And you can see that this has units d squared times volume divided by volume. So now I have to calculate these things. Okay? And I realize that I'm running out of time, so I'm not going to push this calculation. But I'm going to ask you, I'm going to do this on Friday, but I'm going to ask you to do it before Friday. That's your homework for tonight. Right? It's just a little thing to take you back. And this is an interesting number. This is going to be kind of an interesting number. It says, what is the average distance, the average of the square distance of any point in the sphere to the origin of the sphere? That's an interesting geometric property. Because now you can say, how would that differ if I had a plate, a pancake, or a cylinder, or a football, or whatever? Right? How does that change depending on the object we're thinking about? You can, by the way, here's a simple one. Do this for the sphere and do this for the cube. Do it for a sphere and do it for a cube. Right? See what the difference is. Okay? This will lead to center of mass and centroid and a moment of inertia. Hi.
We use variables x, y, and z to describe three-dimensional space, but how would we describe it for
Well, that's next.
Okay.
Give me till Monday.
Okay.
Okay? Yeah, that's a Monday thing. Awesome. Hi there.
I just registered for this section.
Uh-huh.
So I'm wondering how can I make up for the 2 quizzes that I missed?
You can't. Sorry. I don't know.
So I get zeros for that?
Yeah, we drop 1 quiz.
So I'll get 0 for another one?
Yep. This section has been open. We had lots of room in it. And I know that everybody was encouraged not to be on the wait list for the other section and to register for this section. The rules is the rules is the rules. I can't change the rules. You could have come, you could have done the quizzes. I'm sorry. I don't care. It's not my quizzes. I mean, I have my class, right? I don't give exceptions for anything, really. Why didn't you register for my class?
Because I was registered for other section.
And why'd you switch?
But then I got dropped.
You couldn't have been dropped. You were dropped for what reason?
I was dropped because tuition was pretty
And then they dropped you?
from my classes. So then I
Time out. Okay, this is a different situation. I'm sorry. This is a different situation. They dropped you for that reason? That's a different reason. I had a lot of students doing what you were doing because they were on the wait list for the other section. But you were actually registered for the other section?
yeah, and then I got dropped and then I was waitlisted and then I switched.
This is different. I will give you an exception for this case. Okay. That's a stupid reason to drop you. I'm sorry they dropped you for that reason. That's ridiculous. Can you do me a favor? Contact me, show me, take a picture of your quizzes. You did quizzes for the other section?